Okay, so I'm back. The first time I did this, I don't know what happened with the video camera, but it went to sleep, I guess. And I got about to this point and the camera just turned off. And so I wanted to go back there and make sure it was still working. And I just went on and did the relative maximum without you guys. So if you need help with this one, I can go back and show you. But as I was looking through the graph, the table of values, I saw that the relative maximum was at about x equals 2.5. So I was looking at the video, and I'm not quite sure if you guys can actually see what I'm doing on the calculator, so we'll talk about it on Friday if you're struggling with any of that. And again, I can always do a short video, on using the calculator if you want to see it up close and personal. All right, so the next one, we have negative x to the fifth plus 4x to the fourth minus 4x cubed. We graph that. Again, apparently whenever I made this, I was doing extremely well with my graphing calculator. I knew exactly what to do. I was balling out, but today, not so much. So this is as close to that window as I can get. So we can see here, we're going to have a relative minimum right here and a relative maximum right here. The thing that you need to make sure you note, when we look at this, it looks like we have a relative minimum about at x equals 2, but because this is a zoomed in picture of the graph, this is actually 0.5, so this is actually going to look like x equals 1. Alright, so whenever I failed to do the video before, I was like, oh yeah, this looks like we're going to have a relative minimum, x equals 2 and x equals 4. So just make sure you can use this, and by all means do use the graph, look at it, see what's going to happen. But make sure you remember, if you zoom in, these lines here may be factored differently. It may be a factor of 0.5 instead of just 1, 2, 3, 4, 5. So if we go to our table of values, and we're in the negatives here. So as you can see, it's getting smaller. So we start at negative 1.5. So it's getting smaller and smaller. So we're at 9, and then we're at 0.78, 0, still getting smaller, negative 0.2, negative 1, and then all of a sudden it's at negative 0.8. So we had x equals 1, y equals negative 1, and all of a sudden x equals 1.5, we have y equals negative 0.8438. So that all of a sudden is getting bigger. So we can say we have a relative minimum at x equals, what was it? About x equals 1. And again, if you were doing this on your calculator, which we'll do later on, or if you had a smaller step, on your x's, so instead of going from 1 to 1.5, if you went from 1 to 1.1 to 1.2 to 1.3 to 1.4, you could see more exactly where that relative minimum is. But again, this is an estimate, so x equals 1, that's good enough. All right, so then we go back here. We keep going, and so it's getting bigger here. So from negative 1 to negative 0.8, that's getting bigger. Then it goes to 0, so that's still getting bigger. But then all of a sudden, at x equals 2 and y equals 0, that's the highest point right here. That's where we are here. So we can say there's a relative maximum at x equals 2. All right, so that's basically how you do those kinds of problems when you're just estimating. Now, that's about where we were last class. We got to that point last class. Now, this is the new stuff. So if you are trying to fast forward, stop. This is where you need to be. This is the new material, okay? So we're going to use a graphing calculator to approximate the extrema. All right, I was just making sure the camera was still rolling. All right, we're good to go. You guys still see my beautiful, beautiful face, right? Okay, so if we plug this in, we have negative 4x cubed minus 8x squared plus 9x minus 4. Minus 4. And we graph it. Should look a little something like that. We can zoom. Let's see if that works better. No, it doesn't work. Now it's scrolling. Okay, so here's our graph. This is as good as it's going to get. Here you can see it dips down. It dips down here. So there's going to be a relative minimum somewhere down here, and there's a relative maximum somewhere up here. So to do this on our calculator, instead of guesstimating, instead of saying, it looks about like that, we can actually go to calculate on our calculator here. So second trace, and then we can find our minimum, so number 3. And now it asks, if you're watching this, it would be great if you try to do this with me. It asks for your left bound. That means it wants it to the left of where you think the minimum is. So we need to scroll to the left until your blinking dot is to the left of your minimum. So mine's way up here. So you can see it's clearly on the left side of where we think our minimum is going to be. So we press enter, then we go to the left, or go back to the right, and now our blinking dot, where did he go? There we go. So now we know he's to the right of our relative minimum. So we press enter, and now it asks us if we want to guess. So we press enter again. And so now it says our minimum is at about 1.76. All right, so we have a relative minimum at x equals negative 1.76. So that's a heck of a lot closer than what we had before when we were just saying, maybe negative 1, maybe negative 2, maybe negative 1.5. So this is a little bit more accurate. All right, so the same thing we can do with our maximum. We can go to second trace, and instead of going to 3, we go down to 4 to maximum. Press enter. Same exact way. We want to find our blinking dot. We found him. We want to make sure he's on the left of our maximum. Press enter. Now I want to go to the right of our maximum. Press enter. Enter again. And so now we should have a maximum at about x equals 0.43. So a relative max at x equals 0.43. All right, so easy enough. Again, if you need more help on this, just shoot me an email, and I'd be more than happy to see you one-on-one or to do a video for it. All right, so now we got one last thing for Extrema, and then we're going to do average rates of change, and then that's it. We're done. You're ready to start the homework. For this one, it's a word problem. Not very fun, I know, but it's really not that bad when you look at the information given. All right, so let's read it together. Suppose each of the 75 orange trees in a Florida grove produces 400 oranges per season. Also suppose that for each additional tree planted in the orchard, the yield per tree decreases by 2 oranges. How many additional trees should be planted to achieve the greater total yield? All right, so if you have your books, or you can go on that super cool webpage I have, on the super cool webpage I posted, you can find it on the computer. You can see that they work this problem in the book. So if I'm going through it too fast and you're saying, oh my goodness, I have no idea where she got that stuff, go to your book. This problem's in there. You can see it step by step. All right, so the first thing we should see, very first thing we should ask ourselves is, what is it asking for? We want to know what the question is asking. So how many additional trees should be planted to achieve the greater total yield? So we can just say x equals our additional trees. That's what we're trying to find. That's what our question is. We want to know how many more trees should we plant. So x is going to be our additional trees. That's what we add to what we already have. So we have 75 orange trees already. We already have that much. Then we're saying we have a original amount of 75 orange trees, and those trees produce 400 oranges per season. But the kicker is that for each additional tree planted in the orchard, the yield per tree decreases by 2 oranges. All right, so those are the 3 bits of information that we need to take into effect here. All right, so for our function, we're going to say it's just going to be p of x. It's going to be, the first thing we're trying to find is how many additional trees. So we have 75 plus x, right? That's what that's the basic thing of what we're trying to find. But there's also another parameter that it gave us. We have 400 oranges that we get per season. But what it says here, for each additional tree, for every tree that we plant after that 75, we're going to lose 2 oranges per tree. So we need to say 400 minus 2x, because remember our x is our additional trees. So we're going to lose 2 oranges per tree. So now you don't even have to FOIL this out. We can just go straight to our calculator and plug this bad boy in, and we would get 75 plus x times 400 minus 2x and graph it. And if your screen looks like this, it's because you need to zoom way out. So maybe zoom to fit. Okay. We got zoom. So what I did here, all right, let's just start over, because it takes a lot of finagling to get this right. So just start over with me, go to zoom standard. So this is what your window looked like when you first try to pull it up. This is your standard window. So if you go to zoom, fit, it should just look like this kind of straight line. Well, we should know it's going to be a curve, right? Because we're going to have a quadratic here. We're going to have x squared. So x times negative 2x would be negative 2x squared. So if we go to zoom and we just say zoom out, we enter. So now you can see it's, kind of got that parabola shape to it. So that's kind of what we wanted to see. So now that we have our formula, we have the graph, now it kind of looks like what we've been doing before, right? We're wanting to know how many additional trees should be planted to achieve the greater total yield. So really all we're doing, finding our x value, that's that gets our relative maximum, or actually this would be an absolute maximum because it never gets higher than that. So we can just go second trace, find our maximum, do our left bound, then go over, do our right bound, and then guess it. And so on your calculator, it should say a maximum at x equals negative 60, at x equals 62.5, and your y equals 37,812.5. So our x equals 62.5, and our y equals, good grief, 37,812.5. All right, so now what it asks is for how many additional trees should be planted to achieve, the greatest yield. So all we would say is the maximum is when we have 62 trees planted. To put that in words, we would say to achieve a greater yield of oranges, we should plant 62 trees. Okay, so that's what that question is asking for. That's the answer that they wanted us to give. But if they were asked to, what is the greatest yield? If we planted 62 trees, how many oranges would we get? Well, that's our y value here. So if it asks for, try and find the greatest amount of oranges that we could get if we planted the maximum amount of trees that we could, then our answer would then be 37,812 oranges. So that would be our maximum yield. All right, so now, last thing. We only have one more slide to go after this. Almost there. Okay, so begin to stress how important this part is for calculus. We just did an entire chapter on it, basically. You can find the average rate of change on a curve. And you may not think that that's super important, but actually it gets pretty important when you get to calculus. So you can find the average rate of change. So the average rate of change between any 2 points on the graph of f is the slope of the line through these points. So if you're reading this from your book, or if you can maybe read it from this video, this should be pretty easy. You should know what all these words mean. So the average rate of change between any 2 points on the graph. So we're going to pick 2 points on this curve, on the graph that we have, is the slope. You know how to find the slope. It's just rise over run, the change in y over the change in x. So the slope of the line through these points. So you have this curve. Now you're wanting to find the slope of the new line. Now this line is called a secant line. It's very important that you remember that definition, a secant line. So in calculus, what we're actually going to do is we have these 2 points. They seem pretty far apart now, but what we're going to do is eventually get closer and closer and closer to this point here, and it's actually going to be the slope of the tangent line. So we can find the instantaneous rate of change. I know, you're super excited. You can't wait to get to calculus. But that's where this is going. So we're going to find the slope of the secant line, where it's the change in y over the change in x. All right, let me make sure the video is still going. Good to go. Oh man, this is going to be great. It's not even 4:30 yet. I'm almost out of here. This is going to be good. All right, so now we're going to find the average rate of change of this function, negative x cubed plus 3x on each interval. So what this interval is saying, it's saying that we're going from -2, x equals -2, to x equals -1. So our x1 equals -2. Our x2 equals -1. All right, so x1, x2. Easy enough, right? But as you know, to find the slope of any line, you have to have the change in y over the change in x. So we still need to find our y values. So all we do is plug our x values into our function. So to get y1, we have -2 cubed plus 3 times -2. And remember, you have a negative and a negative on the outside, a negative on the inside. So -2 cubed is -8, because remember, -2 times -2 is +4 times -2 is -8. So now you have -8, so that becomes a positive. Then -6. Let me get this whole thing down. So then your y1 value is going to be 2. All right, so we have x1, y1. Now let's get y2. So y2 equals -1 cubed plus 3 times -1. So that's going to end up being -1 cubed. It will remain -1, but the negative's on the outside, so that becomes a positive. This is going to be -3, so that's going to equal -2. Now to do our slope of our secant line, it's the change in y over the change in x, so that's going to be y2 minus y1. So we have y2 minus y1 over x2 minus x1 equals -2 minus 2, right? Divided by -1 minus -2, so it's going to be a plus there. So we're going to have -4 over 1. So our slope for our secant line is going to be -4. All right, so now we have another one that we can do. So if our function is -x cubed plus 3x, right? Yep. Now we can find our slope of this secant line. If we want to find the slope of the secant line on this interval. So our x1 is going to be 0, just found it right here, and our x2 will be 1. So again, we have to find our y1 and our y2. So our y1 will just be -0 cubed plus 3 times 0. Well, that's easy enough. y1 equals 0. Our y2 will equal -1 cubed plus 3 times 1. So our y2 will equal -1 plus 3. So y2 equals 2. So now again, to find the slope of our secant line, that's S-E-C-A-N-T, secant, it's going to be change in y, so 2 minus 0, over change in x, which is 1 minus 0. So our slope will be 2. And that's it, you guys. Hopefully you can complete the homework now with a sense of ease and confidence. If you have any questions, just let me know. And Friday, you will have your notebook quiz, and Miss Campbell will be teaching the lesson. See you guys then.